For the first time, direct evidence of a solid inner core has been obtained on Mars. Seismologists working with data from the InSight mission have determined that there is a solid core at the center of the planet with a radius of about 600 kilometers. This is the first direct seismic indication of a solid planetary core. Prior to this discovery, the solid part of the Martian core was only hypothesized but not confirmed. The key to the discovery was provided by Marsquakes recorded by the mission's Sol seismometer. Scientists identified two types of waves. Some passed through the deepest regions of the core, while others reflected from the boundary between the solid core and the liquid outer shell. Their arrival times and waveforms match the predictions of models that include a solid core at the center. This provided reliable confirmation of the existence of a solid core. The analysis showed that the speed of wave propagation within the core increases by approximately 30% when transitioning from the liquid to the solid part, while the density increases by only 7 plus or minus 5%. Such a contrast indicates that the core of Mars is not composed solely of iron and nickel. It must contain light elements, sulfur, oxygen, and carbon. The model that best fits the data suggests a solid core enriched with iron oxide, with a content of 12 to 16% sulfur, 6.7 to 9% oxygen, and no more than 3.8% carbon. It is noteworthy that the proportions for Earth and Mars turned out to be similar. The inner core occupies about 19% of Earth's radius and 18% of Mars's radius. However, the geological histories of the two planets are different. On Earth, the crystallization of iron and light elements still sustains the magnetic field, while on Mars, it disappeared billions of years ago. The authors of the study believe that cooling in the Martian interior is proceeding too slowly and crystallization is not active enough to power the planetary dynamo. The detection of a solid inner core is an important step in understanding the evolution of the red planet. It now allows for a more accurate estimation of when crystallization began in its interior, why the global magnetic field disappeared, and how these processes relate to the history of other planets and moons in the solar system. The obtained parameters will form the basis for future models of the structure and dynamics of terrestrial planets.